Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 36 today and we are discussing about cylindrical punch being pulled off an elastic half space. So, here we have these references that I am presenting to you from time to time and we can refer to it. So, in the last lecture we discussed about a general ellipsoidal concave shape and we derived what will be the pressure distribution for that concave shape, concave head of this ellipsoidal head of this concave shaped indenter, and we also obtained the expression for the pull off load. And remember that we had also obtained that what will be the value of H max, that means when there is a pull off load is maximized, what will be the optimum shape of this concave head, that also we had deduced in some previous lecture. So, today I like to discuss about an interesting matter, in which case instead of one indenter we have multiple indenters. So, what it means is that suppose we have got one indenter and this has a radius of a, but instead of that so the area of this is pi a square, and let us say we have got several indenter having radius, let us say here actually I represent by r, I guess, several indenter in which case a actually. So, this is capital R, radius capital R I represent. Let me write it capital R here and here capital A, and this is A, right. So, instead of single indenter we have got several such indenters. So, we will like to know that if multiplicity of the indenters can help increase in the pull off load. So, what it means is that we have got, let us say, one indenter like that, and let us say we have got several indenters of contact radius A. So, in a sense what I am doing is I am actually splitting this total contact radius A into smaller indenters. So, I have got n into pi a square is equal to pi r square. Instead of one single indenter we have got n number of several indenters, and such that this A now will be equal to r by square root of n, that is the idea. And now let us say that we have got this flat plate indenter of radius r, for which case this pull off load is given by this. So, for a single, this is for a single indenter. Now, suppose this indenter radius we have is a, and let us say indenter radius is a, and there are n number of indenters. So, indenter radius is a and there are n number of indenters, then this Fc will be equal to what? N into this is square root of 8 pi E star, and instead of r we will have what? We will have the small a. So, it is r will be replaced by a cube W a, like that. So, we have got now a smaller radius. So, that is what is shown here. So, here instead of a r we have got the a here, and so now a is equal to r by square root of n. So, r cube by n to the power 3 by 2 into W a, it is the work of adhesion. So, you see instead of we are what I am considering, that instead of one single indenter we have split this contact area into smaller indenters and of length of radius a, and because of which what is this pull off load that is required. So, pull off load now you see it varies with n to the power 1 upon 4. So, of course, if it is n is equal to 1 this is this value, but now that we have used several indenters keeping the total area constant. So, the total area remains constant, the pull off load actually increases with n number of indenters to the power 1 upon 4, right. So, that means that suppose you have n is equal to 10 to the power 4, right, then the pull off load will actually increase by 10 times, right. Instead of 1 okay, keeping the total area constant, if I can increase the number of indenters, okay, so that means make this indenter diameter smaller and such that n goes to 10 to the power 4, and then the Fc therefore will increase by 10 times, that is not small. So now this is for this particular indenter, which is a flat plate indenter. We like to see what happens if the indenter head is not flat, but let us say it is a convex, spherical convex indenter, okay, then what happens? So in that case again we have got this R is the one spherical indenter as a single, and we have split it into several indenters. So again here this A will be R by square root of n, let us say n is the number of indenters. So here again I will have n into 3 by 2 and pi, and A will be equal to R by square root of n into WA. So here again we can see that n to the power half into 3 by 2 into pi, okay, into 3 by pi into R into W A, that will be we know that the pool of load in this JKR type contact mechanics for a spherical indenter is given by 3 by 2 pi R W A, and now since we have divided this contact area, of course keeping the contact area or the radial not contact area, I should say the sphere radius same. So that means the area taken by this, okay, this spherical shape, that area that remains constant. Keeping that constant, okay, we have divided into small parts. So the Fc now pool of load actually goes as square root of n, again amplification. Yeah, so this can also be done for, let us say, for a concave spherical indenter. So in the concave spherical indenter case, let us say that we replace this one indenter by several indenters, such that this here it is capital H and R, here it is replaced by small n h, such that let us say, okay, R by H is equal to A by H. So this ratio remains constant. Keeping that ratio constant and keeping the total area also constant, okay, let us say that we replace one this concave spherical indenter by several, okay, n number of such indenters, so that pi R square is n pi A square, and so here n will be equal to again R over square root of n. So now pool of load for a single indenter is given by like this. So let us do it for n number of indenters. So let us say it is n will be minus n into, this is 8 E star, in place of R I have A, in place of capital H I have small h, divided by 3, plus here I will have 8 pi E star, instead of R I have got A cube W A, and let me now substitute for A and H. So it will be minus, it is n, this ratio will remain constant. So 8 E star, 8 E star by 3, and remember this n, A is equal to R by square root of n. So therefore H will also be equal to capital H by square root of n, right, because A by H and R by H, that ratio remains constant. So E star, so A is equal to R by square root of n, and here H is equal to into H into square root of n, plus this is 8 pi E star, and instead of A I have R by square root of n, R by square root of n into cube into W A, that is the work of adhesion, okay. So what I will have is equal to minus, this is 1 upon n, it is n gets cancelled. So here I get 8 E star into R by 3 and H here, plus here it is n, it is 3 by 2, 3 by 4 here. So it is 1, this is n by n to the power 1 by 4 into, this is 8 pi E star into R cube into W A. So yeah, this concave head portion that does not appear to contribute to this enhancement or amplification of this pulling load, but this portion, this part, the second part, okay, that comes from this flat flat indenter derivation that does depend upon n to the power 1 upon 4. So, it gives like that. Let us take a problem. So, here an insect weighing 10 grams has to stick to a surface, and why insect? Because insects have got this adhesive pad. Adhesive pad actually consists of several small features, okay, topographical features, looks like indenters. So, that is why. Now, the adhesive pad of its feet has a work of adhesion of 100 millijoule per meter square, okay, with this surface. So, it actually working upside down. Okay. The adhesive pad is composed of a number of microscopic pillars, that is what I was saying you, having the shape of concave indenters. The physical and geometrical properties of the adhesive pad is described here. What is the minimum number of pillars that are expected to constitute the adhesive pad of the insect, so that it can balance its own weight? So, it needs to balance its own weight. So, its own weight is P is equal to 10 grams. So, 10 into 10 to the power minus 3 kgs into 9.81 Newton. So, this will be equal to, let us say, about 10 to the power minus 2 into close to about 10 to the power minus 1 Newton. So, 0.1 Newton it needs to hold, okay, by using its adhesive pad. Okay. So, of course, it has got several feet, but all taking on to all the feet, okay, how many adhesive pad is required, that is what we are looking at. So, here all the values are given, and now let us try to see if we can say something about the number of pillars that is required. So, here F will be given as 8 E star R H by 3. So, let is will be equal to, let us say, 8 into E star is 0.1. So, E star needs to be found out. So, let me find it out E star here. So, let us say E star is equal to 0.1 into 10 to the power minus 6 megapascal, 1 minus 0.47 whole square. So, I do not know exactly how much it is, but it should come out to be some nice number. So, let us see E star, okay, I did not find out separately, but that is okay. So, E star is like this. So, let me keep the E star into R into H. So, R is equal to 1 millimeter 10 to the power minus 3, and H is equal to 0.1 millimeter 10 to the power minus 3 by 3, I guess, 3 here, plus n to the power 1 upon 4, n to the power 1 upon 4, and then I have square root of 8 pi E star, 8 pi into again that E star into R cube. R is 10 to the power minus 3 cube, R cube into WA, this is 100 into 10 to the power minus 3. So, this whole thing should be equal to about 0.1 Newton, that is all it means. Of course, E star can be found out, and then finally, I have done all that. So, it comes out to be 0.1 Newton. So, yeah, so it comes out to be about n is equal to 179. So, 0.1 is equal to 0.0342 plus this term comes out to be 0.018. So, you can use your calculator and find out if I have done it correctly, and then finally, this n comes out to be very close to 180 and like that. So, this insect needs about let us say 200 such pillars, okay, by which will be good enough for it to support its own weight when it has to walk upside down, okay, on a surface. And this is an interesting result again published in this particular paper, and where this author show that these insects, as the mass increases, animals mass increase from beetle to fly to spider to gecko, okay, this every case they have got this adhesive pad. In every case they have this adhesive pad of particular shape. It is not completely flat, there is some curvature there. For example, over here looks like it is some concave, but remember that this adhesive pad has to work in different types of habitat. Some case it will be flat, some case it will be vertical wall, okay, sometimes it is working upside down, and so therefore, this adhesive pads has to have a shape which will not be exactly ellipsoidal or exactly spherical, concave shaped like that. And some case it is, we have just considered the pull of load, normal load, but in many cases or most cases it will be shear load. Okay. So both normal and shear load has to be taken into account. So the adhesive pads are, design of the adhesive pads in nature is, okay, is therefore optimized, okay, by through evolution. But what we can see is that the number, density of these pillars, okay, on this adhesive pad of this feet, that varies, okay, that varies from here to here. So it is, okay, some scale is also there, and here it is written actually number of seta, we call this hairs as seta per 100 micrometer square, that increases. We can see this is a log plot quite extensively, and for lizards the number of such pillars per unit area is maximum. So this analysis that we present so far kinds of captures this observation in nature. So the physics and in all these cases, another thing that I need to tell is that we consider essentially the dry adhesion, okay, and this for this inkjet, okay. Of course they have some wet adhesion also possible on the cases, but these cases that the picture is given over here, mostly these are dry adhesion, and in that case they have this density of these pillars in their feet by like this, and this the general observation is that the mass increases, the number of pillars that also increases. So this insects, by using this contact splitting principle, can increase the pull of load that is required to separate them from their substrate or from in their habitats. So there is one thing another thing we have want to discuss. So you see, in all these cases we considered deformable, okay, indenter and the deformable substrates, and we have essentially used this idea of effective modulus 1 upon this 1 minus sigma 1 square by E1 plus 1 minus sigma 2 square by E2, that was equal to 1 by E. So that was that effective modulus thing that we discussed, okay, E star and like that. So so it means like at least one of the members, contacting members, was deformable. Now let us say that two rigid spheres, so they are not deformable, okay, they are separated by a distance h, and the h distance is such that this intermolecular forces that act, so there is an adhesion because between them, okay, that holds. So in that case, what is the force required to separate them, that we would like to find out. So far we discussed about deformable objects, but let us leave aside these deformable objects or adhesives for a while. Let us consider that what will be the force, okay, required to separate, force per unit area required to separate these two objects or spherical indenters, let us say, or spherical rigid spheres, let us say, which are rigid, so they are not deformable. For this we need to know this intermolecular force, and let us say the intermolecular force is this van der Waals force of attraction or Lennard-Jones potential and blah blah. So we have discussed about to some extent this issues about in lecture 17, you can go through that. From that van der Waals force of attraction, the surface energy, Hamakar constant, how Hamakar constant is related to the surface energy and all that. Okay, we have discussed it in quite, not very detail, but to some extent. For detail you can get some nice books for on interfacial phenomena and all that, and you can read it. But for our course purposes, whatever we required we have kind of discussed. So here we have also said this van der Waals force of attraction, the intermolecular potential energy goes something like this. So there is an attractive part and then there is a repulsive part. So this is the attractive part and this is the repulsive part, right? So repulsive part, because that when when they come very close, then there is a kind of repulsion that happens, called a bond repulsion, all that, and the energy diagram will look something like this, okay, with respect to distance. So it will first decrease here, and then there is a minimal distance that is attained, and after that there is a repulsion over here. So normally this is the equilibrium distance and like that. So this is the equilibrium distance epsilon. It values it about 3 to 6 angstrom. Okay, it might be somewhat small also, but it's like this. So now question is that this is the Lennard-Jones potential. From that, this is the expression of this force, this between these two molecules, let's say. Okay. Now what we did is that we integrated these molecules over an area and all that. And finally, we showed that if there is a sphere there which is at a distance z, let us say, from a surface flat plate, then this force of attraction is given by this expression, where A12 is 1 is the sphere, let us say, 2 is the substrate, let us say. So, A12 is the Hamakar constant, R is the radius of this particular sphere, and what is the attractive force between them? Now, that is given by this particular expression, which is z square dependent, inverse z square dependent. So, z decreases, the force of attraction increase, something like that. So, we have kind of, so it is it will finally reach this distance z0, at which there will be repulsion will be very high, and so it will not go beyond that. That is a kind of uniform equilibrium z equilibrium gap that will be attained. And if it is two parallel plates, then this quantity is given by this expression. Okay, this is the force per unit area. This is the force per unit actor area, that will be given by A12 by 6 z cube. And for per unit area calculation, there is a pi here, I have missed here, there should be pi here. Okay, A12 by 6 pi z cube, and so per unit area. So, now you can find out the total energy required to take this, separate these two surfaces from, let us say, that equilibrium distance which is z0 to infinity. So, from z0 to infinity you need to separate it. Okay. So, that is the energy required to separate these two surfaces. So, when we say that two surfaces are adhered in contact, basically they have a gap between them, and that is equal to this quantity z0, and now we want to separate them. So, this z0 to z goes from z0 to infinity. So, the energy spent in doing that is actually this quantity per unit area, A12 by 12 pi z0 square. Now, that actually is equal to my work of adhesion that we have. So, work of adhesion, Hamakar constant, z0, these are all related, and this can be related by this expression over here. So, in a sense, what we discussed here basically is that what is the force required, a force of attachment attractive between the sphere and a flat plate, or let us say two flat plates. And so, let us say that Lennard-Jones force of attraction per unit area between two rigid sphere is separated by a distance h, is given by F is equal to sigma h. So, basically it is sigma as a function of h. This is the attractive force per unit area between two rigid spheres. So, the h is given by this particular gap. Okay. So, this is the gap by which sigma. So, it is a flat plate, this is a sphere, and this is also a sphere, this is R1, this is R2, these are two both the rigid. So, there is no deformation there. Now, this portion of the surface of the sphere has been taken, this is the elemental portion. So, this element has this radius r and this quantity dr, and this is at a distance h from another element over here on this sphere 2. Here this is again the same thing. So, now what is the force between, so this force between them, okay, is given by this function sigma h. So, therefore, what is the total force that acts between these strips? This is strips, this is a ring actually. So, this will be 2 pi r into dr, that is the area of that particular ring or ring, yeah. So, 2 pi r into dr into sigma h, and now you vary it from 0 to infinity. So, 0 to infinity is the h varies from 0 to infinity, that is all it is. So, the sphere may be considered a parabola. So, that means h is equal to 0 means infinity means they are very close to each other, basically that is what it means. Now, the sphere may be considered a paraboloid, so that the gap needs to be expressed. So, the gap is expressed something like this. So, what it means is, let us say that what is this r delta d 1 by r1. So, that means delta d means, I think I am looking at this distance, this is let us say delta d1 or something like that. So, this delta d1, that if you see, this is equal to this quantity, this is r minus this quantity. Okay. So, this is r minus this quantity, that is equal to this delta d1 here, that is what it is. So, r1 minus, so this height will be square root of r1 square minus r square, that is this quantity. So, therefore, this is r1 minus r1 into 1 minus small r square by r1 square, and we have used this particular approximation considering that r is quite large and all that, and that leads to this particular expression r square by 2 r1 here, and delta d2 will also be then r square by 2 r2, and we add up this all the distance gaps and all that. So, the gaps will be, let us say h0 is the gap here, let us say this gap is h0, something like this, okay, plus delta d1 plus delta 2. So, that defines this particular height h or the gap h between these two thin strips, and that gives rise to this expression h0 plus r square by 2r. So, the force between these two spheres, okay, is that we can actually substitute over here. So, that will be equal to, force will be equal to 0 to infinity into 2 pi r, 2 pi, now r square, not 2 pi, no, I will not write 2. So, it is actually pi instead of r square if I write. So, it will be, let us say, so here let us say dh is equal to, over here d of h is equal to, it will be 1 by 2 r into d of r square. So, here this d of r square, that will be equal to 2 r into d of h, okay, d of r square. So, here f will be equal to 2 pi r into sigma h into dr. So, here I will write something like this, pi and r will be this is sigma of h into d of r square, So, therefore, I will be able to write it here, this is as, let us say 2 r d of r square 2 r, so this is, so yeah, let us say that this is equal to, this is pi and then d of r square is equal to 2 r, and let us say this is 0 to infinity, and this, us say it is sigma of h d of h. So, see, this quantity is actually w, because that we have derived earlier, right. So, what we get here is 2 pi r into w, right, that is what we get. So, in essence, okay, we have this equivalent relative radius of curvature r, and then you have work of adhesion W A, and the force of attraction between them, you get it 2 pi r W A. So, this is the force that is required to separate these two surfaces, right. So, that is what it is for, and this particular relation is called this DMT model, yeah. So, 2 pi r W A, and this relation is known as Deryaguin-Muller and Toporov, I think 1975 they came out with, this is called the DMT model. So, this is that DMT model, and we will show you that there is an issue about DMT model where the force is given as 2 pi r W A, okay, and how it work relates to, let us say, the JKR model, okay, we will we'll talk about it in the next lecture. Thank you for today.